So here we are on question 7 of the homework set. And yes, this question is about the midterm. There are 250 sad students in the class because the midterm was difficult and it was unfair. So there are a bunch of people in the class who are sad. Well, 250 out of 450 students. And so the professor comes up with a brilliant plan to send friendly volunteers, happy people, to randomly give hugs to people in the class, because hugs always make people feel better. So they don't choose sad people specifically. Actually, it's independent of who they choose people independent of whether they are sad or happy. So each person just walks into the crowd and hugs somebody randomly. So the professor wants to try to make sure that any sad person in the entire class, all the sad people are hugged. So he starts sending people until the sad people are all hugged. At least this is question 1. So he sends people in until all the sad people are hugged. So what is the expectation of the number of volunteers required so that all the sad people are hugged? So if you've read the notes, this question is very similar to the coupon collector problem. The coupon collector problem is set up as follows. So you have n different coupons which you want to collect, and they come in, let's say, cereal boxes. So every day you go buy a cereal box and pull out the coupon. Now the coupon inside the cereal box has a 1 over n probability of being any given coupon. So the coupon which you pick out of your cereal box is randomly distributed and uniformly distributed over all possible coupons. So the question asks you how many boxes you are expected to buy, or you would probably need to buy before you have all the coupons. So this is very similar to that problem, but except that in the coupon collector problem you had 450. If you're comparing this to the coupon collector problem, you had 450 coupons and you have to collect all 450 of them. In this case, you have 450 students and you have to only make sure that you collect, or you make sure that only 250 of them need to get hugs, because the other 200 students don't really feel sad. So it's like the coupon collector problem, but it's different in the sense that you're not collecting all the students, so you're not hugging all the students. You are only hugging a subset of all the students. But as it turns out, you can go about doing this almost exactly the same way as you would do the coupon collector problem. So first, let's just name some variables. Let m be, because we don't want to work with numbers, let's just substitute the numbers in the end. Number of sad students and total number of students. Right? So let x be the, RV denoting number of volunteers. Right? So you have x to be the random variable, which denotes the number of people the professor has to send so that all the sad students have been hugged. So how do we go about finding the expectation of x? So in order to do this, let's break up x into smaller random variables which we can think about and reason about easily. So let's look at it this way. Let's send people so that the first sad student is hugged. So we keep sending volunteers, or the professor keeps sending volunteers until the first sad student is hugged. After the first sad student is hugged, the professor sends more volunteers until the second sad student is hugged. So he keeps doing this until all the sad students are hugged. So basically, he waits until the ith sad student is hugged, and then he sends the next bunch for the I plus 1th sad student. So let xi be a random variable for number of volunteers to hug new, let's say, ith new sad student after I minus 1 sad students are, whoa, that was bad, I minus 1 sad students are hugged. right? That's a long statement, but yeah. So basically, it's the number of volunteers you send between the ith SAT student being hugged and the I+1 SAT student being hugged, or rather, between the I-1 SAT student being hugged and the ith SAT student being hugged. So what is x going to be equal to? X is obviously going to be equal to x1 plus x2 all the way to plus xm, right? Because the total number of SAT students, total number of volunteers you need to hug all the SAT students is the sum of all the is the sum of the number of volunteers you need to hug the first SAT student plus the number of volunteers you need to hug the second SAT student after that, plus the third, plus all the way till the last SAT student, right? Now each and every one of these random variables we can reason about very easily, right? So let's just look at xi. So you know that you've hugged I-1 SAT students. So how is this distributed? As in, how is hugging the ith, how is the number of students you need to send so that the ith new SAT student is hugged? How is that random variable distributed? So you know that you don't need to hug, you know that you don't need to hug how many students? You don't need to hug, first of all, you don't need to hug the n minus m happy students, plus you don't need to hug the I-1 students you've already hugged, right? Don't need to hug these many students, which means that the probability that that you actually hug a new SAT student is going to be probability of hugging new SAT student after I-1 SAT students is going to be equal to, so you have m minus I-1 over n, right? So you have total number of SAT students, the total number of SAT students left to be hugged is m minus I-1 over n. And the total number of students is n. So the probability of hugging a new SAT student after I-1 SAT students have already been hugged is just m minus I-1 over n. And what we're going to do is we're going to keep sending volunteers until this SAT student is hugged. So maybe we're gonna fail the first time, maybe we're gonna fail the second time, maybe the third time we're gonna find a new SAT student, right? So the way xi is distributed is obviously geometric of parameter what? M minus I plus 1. I've just opened the brackets, right? So this is the probability of getting a new SAT student, and until we are actually finding a new SAT student, we're going to keep sending volunteers. So xi is distributed as geometric as follows. Okay, so I'm going to clear the screen now, and I hope you guys will remember the definition of xi after I clear the screen. I'll write it up again. Right, so I'll write it up again. Xi is distributed as a geom of m minus I plus 1 over n. So yeah, xi is just the number of volunteers you need to send after hugging the I-1 SAT student to the ith new SAT student. Now you know x is equal to, I'm going to write this as a summation from I is equal to 1 to m xi, right? So now let's look at the expectation of x, which is what we need to calculate, which is equal to expectation of sum from I is equal to 1 to m xi. And from linearity of expectation, you can just pull the summation out, which is equal to I is equal to 1 to m expectation of xi, right? And what do you know about the expectation of xi, given that xi is a geometric random variable? What is the expectation of a geometric random variable? It's just 1 over the parameter. So it's just n over m minus I plus 1. So the denominator looks a little weird, right? And in order to try to fix the way it looks, let's just try to reverse the direction of the sum, as in let's just go from I is equal to m to 1 and see what happens. Or before I write that down, I'm just going to argue what happens. So when I is equal to m, the entire denominator is going to be 1. And when I is equal to 1, the entire denominator is going to be m. So if you go the other way around, you're just going to find that the denominator goes from 1 to m, right? So I'm just going to rewrite the sum as I is equal to 1 to m n over I, right? because it's the same thing. Going backwards, it's going to be the same thing, right? So yeah, and this one from the coupon collector problem is something which we've seen before. Well, not just from the coupon collector problem, but just in general, and it's given in the notes. That I'm just going to write it here. I is equal to 1 to m 1 over I is equal to, I wouldn't say is equal to, is approximately equal to ln of m plus some gamma, where gamma is called Euler's constant, approximately equal to 0.5772, right? So the summation from I is equal to 1 to m 1 over I is approximately equal to ln m plus some gamma, which is equal to n times, so going back to the expectation of x, I'm going to continue n times 1 over m 1 over I. This is equal to, from, well, again I shouldn't say equal to, which is approximately equal to n times ln of m plus gamma. Now let's plug in the values of n and m. So when we plug in the values, we get 450 times ln of 250 plus 0.5772 approximately, which comes out to be around 2744.397, whatever. So this, obviously we can't send a fractional number of volunteers, so this is going to be equal to 2745, let's say. So the professor would approximately or is expected to send around 2745 volunteers before all 250 students or SAT students have been hugged. Alright, so that's it for question 1. Now let's move on to question 2.